Hi guys, welcome to Safi Mixed. In this video, I would talk about the representation of vectors in a Cartesian coordinate system. And you will see that two different ways are used to represent a vector in Cartesian coordinate system. And I'll talk about both of these ways. So to this end, I first draw the coordinate axes. I call this x-axis, this one y-axis, this is x prime, and this is y prime. And I draw a vector here at certain position like this one. Let me draw this to this point and this a little more lengthy like this. Then in order to locate the position of the initial point or tail of the vector and similarly terminal point or head of the vector, what I do, I draw perpendicular lines on the axis. From this point I draw a perpendicular line and let this is the point x1, that is the value on the x-axis is x1. This is a real number, and similarly this is a real number. I call this y1. Then the tail of the vector is written as a point with values x1 and y1. And similarly, to find the position of the vector, of the terminal point of the vector or head of the vector on the coordinate plane, I drop a perpendicular from this point on x-axis. Let me represent this with x2, and this point is then y2. Then the point on this plane, which I represent with q, is written as x2 y2. That is the coordinate. The coordinates values of p are x1 is along x-axis, y1 is along y-axis, and similarly the coordinates values of point q are x2 and y2. From these values, we see that the length of the vector along x-axis is this much, right? So I can write this as x, the length along x-axis. Let me write this over here. The length of the vector along x-axis is then written as x2 minus x1. That is, this point minus this point gives the length of the vector along x-axis, and similarly the length of the vector along y-axis is obtained by subtracting the value from each other, that is y2 minus y1. Once we have the values along x and y-axis, then we represent this vector pq by an ordered pair x and y. So the vector PQ in the coordinate planes is represented by this ordered pair where x is the value along x-axis and y is the value along y-axis, and we see x and y are obtained by subtracting the tail from the head along the two axes. And in order to avoid confusion, sometimes, because we know from our previous videos that this represents an open interval on the coordinate axis, so this is, in most of the book, the representation is changed from the parentheses to these wedge brackets, which is also called angle brackets. So in fact, the vector on a coordinate plane is an ordered pair of real numbers. X and y are real numbers because these two coordinates axes represents the real numbers line. Okay, this is one way of representing the vector, but we know mostly, remember, in coordinate planes we deal with free vectors. Free vectors, we know from one of our previous videos that they are the vectors whose position is not important on a coordinate plane. The only thing, or the only two things that are important, are magnitude of the vector and direction of the vector. So with that concept in view, we can shift this vector from this position to this position. So I would just rub them out. and re-represent the vector from the origin, I represent the vector like this. So then the point P automatically shifts to origin O, and point Q shifts to this position. Now if we look, the coordinates of the origin are 0, 0. That is, we have the origin, the point O, like this. Point O is 0 and 0. That is, the value of x is 0, the value of y is 0. And in order to locate the position of the tip, I draw a perpendicular on the x-axis and let this be x, and then I draw a perpendicular on the y-axis and let this be, I remove them, this I represent with y. Then obviously PQ with respect to origin O is simply written as PQ equals x and y. Then this is this order pair represent vector PQ, not PQ, right? This is now OQ. This is not PQ. Now the vector is replaced with OQ. That is, P has been shifted to the origin of coordinate system. So this is now the line OP. And vector OP is then represented as an ordered pair X and Y. And the magnitude of this vector is simply written as OQ is square root of x squared plus y squared. That is, if the vector is drawn from the origin, we just square the coordinates of the tip of the vector, the coordinates of the head of the vectors, and take the square root. That order pair then provides the information of the magnitude, and this gave us the length of the vector, the magnitude of the vector. So this is one way of representing a vector and coordinate system, and which is in terms of the ordered pair. So we write vectors as an ordered pair of two real numbers on a plane, on a coordinate, and on an xy coordinate plane. Now, there is another way of expression the same vector, another way of representation of the same vector, and that representation is generally used by, is commonly or mostly used by physicists, though that is used by mathematicians, but physicists don't follow this representation of the vector. They mainly follow the one that I'm going to explain now. And what is that? We when we drop this line from this point to this point, we say that the distance from origin to x in fact represent the x component of vector OP, and then we write this component as OP sub x. But this is not a good way of representation. We in fact give a name to the vector. Let me call that name be A. That is, OP is a vector which we represent with A. Then this component is written as A sub x. That is, AX is the component of vector A along x axis. And similarly, the length from this point to this point, which is parallel to this, from this point to this point, these two are parallel, and we just learned that the position of vector is not important, so we can shift this to this point, and we call this part of the vector as AY. That is, AY is the y component of this vector. And now if we follow the addition, the head to tail rule for addition, this in fact is a head to tail addition. We have this vector which is placed from origin to this point, and then we have added the tail. We have placed the tail of this vector with the head of this one, and have finally joined the head of the final vector with the tail of the first vector, and we obtain A. That is, if we look to this procedure, it looks like the addition of vector AX and vector AY through head to tail rule. Okay, that's true, that is the same thing, but we use another name for this process. In fact, we don't have AX and AY. Rather, we have given vector A, and from vector A we obtain AY and AX. So this process of obtaining two vectors, one parallel to x-axis, this vector, and one parallel to y-axis, this one vector, from a given vector is called decomposition of vector into its rectangular components. So we have in fact decomposed vector A into two components. Now, this is one vector, this is another vector, and they make the components of vector. In these components are at right angle to each other. Therefore, we use another special word for these components. We call these rectangular components of a vector. Rectangular means they are perpendicular to each other. So vector AX and AY are perpendicular to each other. Therefore, we call them rectangular components. Now, in this representation, we write the vector as, I would like to write this over here. If we follow the head to tail rule, I can write vector A is AX plus AY. Okay, one we have this representation, order pair, one we have this representation, and again we can write this as an order pair, but this is another way of writing the vectors, the vector algebraically. And we go one step more and represent vector A sub x and A sub y in terms of their magnitudes in their direction. And we know that any vector A can be written as the magnitude of vector times a unit vector. So this unit vector is general, this is in the direction of A, but a unit vector in the direction of x-axis is a special vector because we always consider x-axis to be horizontal. So that unit vector is reserved for representing the horizontal direction. And similarly, a unit vector along y-axis is a special in a sense that that unit vector always represents the vertical, the upward direction or the downward direction. In this sense, special notations are used for those unit vectors. If we write the unit vector along x-axis like this, right? I represent the unit vector along x-axis by the alphabet small I, and similarly the unit vector along y-axis by the alphabet small j. So these are reserved unit vectors. These are special notation that are used for representing horizontal direction and vertical direction. You may see sometimes these are written as E1 and this is written as E2, but I'll not talk about these directions. So at the moment, those are used in vector calculus, but these two representations are sufficient. So using this direction, that means I can write vector AX is AX, the magnitude, I'm not putting the absolute, but just write it in without vector notation, and then I multiply the unit vector I. So now this is a vector with magnitude A sub x and direction I. I stands for the direction along horizontal, along x-axis. And similarly, I can then represent AY in the form AY into J. That is, AY as a vector with magnitude given by the number AY and is parallel or is pointing in the direction of y-axis of the coordinate system. So if I replace these values into this equation, I can then write vector in the form AX I plus AY J. So this is another algebraic representation representation of a vector in Cartesian coordinate system. Now you see there is in fact a one-to-one correspondence between the length and the order pair. The order pair and the components along x and y axis. So this one-to-one correspondence between the length and the ordered pair of a vector allows us to write it in different ways. In the two of these different ways is one this one equation and the other this one equation. So we can use any of these two equations to represent a vector in Cartesian coordinate system. Now, if we have a vector in space, we would then add another axis to our plane xyz, xy, and then the third one would be z. In that case, the ordered pair would be a triple of numbers, and in that case our vector would be something like this. I would like to write this over here. In that case, our vector OQ then would be an ordered pair, a triple of number x, y, and z. And in the algebraic form, in this equation, we would then add another component to write the vector in 3 space in the form of axi plus ayj plus a sub z, and the unit vector along z-axis, the resolved unit vector along z-axis is k, small k. So then we write a vector in 3 space through this one equation, and the magnitude of vector then is the square root of the sum of the squares of the magnitude of these components. That is, if I want to write the magnitude for 3 space vector, then the magnitude OQ is given by square root x squared plus y squared plus z squared. And in terms of these components, the vector A, the magnitude of vector A, which is again this is not P, this is Q. I made this big mistake right from the beginning, so that is Q. Because I'm writing this OQ, so this point is Q, not P. Then the magnitude of this vector is written as square root AX squared plus ay squared plus az squared. We write it like this. I would remove this negative x's so that the equation is well clear. So this way then we find the magnitude of vector. So I would suggest you to memorize this equation for good. The magnitude of vector is obtained by first squaring the components, then adding the components, and then taking the square root. So there are 3 steps in finding the magnitude of a vector. The first, to square the corresponding components of the vector, then add the square of those components with each other, and then after adding, take the square root. So this is a 3-step process. You first square the components separately, then add the components to each other, and then take the square root, and the result of this then gives you the magnitude of vector. Okay, then since we can find the magnitude, then there is another thing that we need to know. Vectors are specified by 2 things, by magnitude and by direction. So we need to know about the direction of the vector as well. Let me write that thing. And we can do that very easily. If this is theta, that is the angle vector A makes with the x-axis of the coordinate system, then we can find this direction, this theta, by using trigonometric ratios. Since this is now AX, this component is AX, and this component is AY, and we have a right angle triangle. So we can straight away resolve by using the trigonometric ratio. We know that perpendicular by hypotenuse is a sine of theta. So we can write AY divided by A equals sine of theta. And from this, I can get A is equal to A sine theta. This is one very important equation. And then from the second ratio, we have AX divided by A equals A cos of theta. From this I can write AX is equal to A cos theta. This is another very important relation. That means, okay, what do we have from these two equations? What we did previously was, in fact, geometrical addition of vector, or the geometrical way of finding the components of vector, and now we are going to do that analytically. If we have given vector A, when I say we have given a vector A, that means we know about the magnitudes of the vector and we know about its direction, that we know about this theta. So if we know about these two quantities, then using this one equation, we know A, we know theta, so we can find the right side of this equation that gives the component AY. So we can find, by using this equation, the component AY, and similarly we can find the component A sub x by using this one equation. So if we have given vector, that means we know the magnitude of vector A and the direction of vector A. We can find analytically the components of the vector. So that's why I would further suggest to memorize this equation. Let me call this equation A and this equation B. So you should memorize these two equations by heart. Now, on the other hand, if we know about the components AY and AX, if we know about the components, we haven't given the vector, we are given the components of the vector, then we can use these two equations to find the magnitude of the vector and direction of the vector. How can we find the magnitude? Let me first square this one equation. I can add this equation squared to write this as A squared sine squared theta, and then I can square this equation to write it AX squared is equal to A squared cos squared theta. And if I now add these two equations, I'll get AX squared plus AY squared, and on this side I'll get A squared, I'm writing first this one, cos squared theta, and then plus A squared sine squared theta. Now, I have A squared common with these two terms on the right of this equation, so I take A squared common and write this as cos squared theta plus sine squared theta. And we know this is the first Pythagorean trigonometric identity, and its value is equal to 1. And if you don't know about this, I will suggest you to watch my videos on trigonometry. And this thing is then equal to 1. And so we are left with A squared. And now if I take the square root of this equation, we get this one equation. Let me take the square root. I want to do it over here. If I take the square root, I'll get AX squared plus AY squared square root, and on this side I would have square root A squared, and this in fact the definition of A mod. So we write the magnitude A mod of vector is in fact equal to, I'm inverting this equation, is AX squared plus AY squared square root. We are back to this equation with this component not in hand. Okay, now we can, that is, if we have given the components of a vector, we can find through this procedure we can find the magnitude of the vector. Now, how can we find the direction of a vector from the components? If we have given the components, then what I do, I just divide equation A with equation B. If I do that, I write AY divided by AX is equal to A sine of theta divided by A cos of theta, right? I divide this equation with this equation. So on this side, I cancel the A in numerator with the A in denominator. And by definition, sine theta over cos theta is then tangent theta. So I write this as tangent of theta. and we have the inverse of these functions, so I can take the inverse to write this as tangent inverse of ay over ax is equal to theta. So theta is now the direction of this vector. That is, if I divide the y component with x, with the y component of a vector with x component of a vector, and then take the inverse of tangent of that result, I get the direction of the vector. So this way we find the magnitude from the components and direction from the components. So now we have two different things. If we have given vector, we use equation A and equation B to find the components. And if we have given, because given vector means we know about the magnitude and about the direction. And if we have given components, then we use this one equation. Since we have given the components, we use this one equation to find the magnitude of the vector, and this one equation to find the direction of the vector. So this way we use the rectangular components of a vector to find the direction and magnitude r. In other words, we use these equations to find the rectangular components of a vector in Cartesian coordinate plane. And obviously, if we have if we have a three-space vector, three-dimensional vector, then we deal with the z component as well. But for the time being, this is sufficient to find the direction of a vector in a plane, and the magnitude of a vector in a plane from the components of the vector. Thanks for watching.